So we now know what to do if we have an equation that's at equilibrium in order to find the equilibrium constant expression value, or the equilibrium constant. And we know that we can take the products raised to their coefficients over the reactants raised to their coefficients, and we can give ourselves a KEQ expression. If we're at equilibrium, we can plug in those values and just find the number pretty easily. But what happens if we're not at equilibrium? And the answer is you would need to use a Rice diagram or an ice diagram in order to set it up. Now, I prefer to call them ice diagrams, but Mr. Kilgore likes to call them Rice diagrams. Ice diagrams stand for initial, change, and equilibrium. And if you are including the R, that would be the reaction up at the top. So we're going to consider a problem right here where we have a reaction, and that reaction is A plus 2B yields C. Now I'm going to start the reaction with 6 molar A and 2.5 molar B. And when the reaction reaches equilibrium, only 5 molar of A remains. Calculate the value of the KEQ. So what we're going to do is set ourselves a Rice diagram. And we start off by writing the reaction up at the top. So we've got A, 2B, and C. And I like to include the coefficients because it helps you to keep track of the changes a little better, because our change is dependent upon the coefficients. Now what I like to do is do some kind of dividing line between the reactants and the products, just to show that where the reactants are, where the products are. Now we're going to follow the steps over here in order to solve this equation, and the first step is to fill in what we know. Alright, so if I read the equation, I know that I have 6 molarity A, so that's initially 6.0 molarity, and 2.5 molarity of B. So that's another initial value. Now, you can make an assumption that if you aren't told anything about one of the reactants or products, then that value must be 0. And you can only assume that for the initial things. Now, we also know that at the end, the molarity of A is 5. So I can fill in at the end, or the equilibrium, this is 5.0 molar. Alright, so that was step 1. The next step is to find the change. So in this case, we have a start and an end for the initial of A and the final of A. So we know that the difference was that it decreased by 1.0 molarity. Now, the change is related to the coefficient, so we need to keep that in mind. The next part is to assign the sign. Okay? So we know that since there's no C in this reaction initially, then our reaction has to proceed so that C gets made. So we know that A and B are going to decrease, so we can fill in the negative signs there, and that the C value has got to increase because you can't have less than 0 of a substance, so that has to go up. Now, step 4 says that we're going to use the coefficients to find the other change values. Now, we know that our mole ratio was 1A to 2B to 1C. So our change is related the same way. We have 1 molarity for A, so if we're looking at our coefficients, our mole ratio, it's 1 to 2, so this is going to be 2 molarity for the change of B, and C is going to also change by 1.0 because that's our ratio, 1 to 2 to 1. The next thing is to find the equilibrium values. So we have 2.5 molarity minus 2 molarity gives us 0.5 molarity, and 0 plus 1 equals 1. Alright, we're almost finished. Now we know our equilibrium values, we can solve and find the KEQ. So our KEQ is equal to the concentration of the product raised to their coefficient over the concentration of the reactants raised to their coefficients. Alright, so we've got C on the top, that's 1.0 molarity. And on the bottom I have A, which is 5.0 molarity, times 0.5, which is squared. And if I solve this, I'm going to find that my KEQ is equal to 0.8. Now, we usually don't keep track of units, but if I wanted to, I would see that our unit is molarity to the -2, or 1 over the molarity squared. Hope this was helpful.